Thompson, Marketing Manager at ITI, and welcome to the Showcase webinar series. Today's webinar is titled Winch, Drag, or Roll. And while that might sound a little bit like a 1980s game show, what you're in for is a few problem-solving rigging workshops, so you're definitely in the right place. All kidding aside, today's webinar should be a lot of fun. I hope everybody received the email containing a link to the 2 reference cards and a workbook that will be needed to follow along with the presentation. If you registered late, you can still access this information by visiting iti.com/showcase-webinar-materials. And I apologize to those who have heard this introduction in the past, but for folks joining us for the first time, I'm going to give a very brief introduction to ITI before handing things over to Mike. ITI is a training and consulting organization, specifically crane rigging and lift management training courses at both client locations and at our 3 state-of-the-art training centers in Woodland, Washington, Memphis, Tennessee, and Edmonton, Alberta. We currently have a presence in the United States, Canada, and Brazil with trainers based in all 3 countries, and we've done work on every continent except for Antarctica. ITI is lucky enough to work with a very, very broad industry base. As the nature of crane rigging and lifting activities go, it's not limited to any specific industry, and you can see that on the slide here. We're really proud to have worked with some of the best organizations in the world, and the fact that the very successful companies you see on the slide there, as well as others who aren't listed, trust us with their crane and rigging operations. It really is something we're proud of, and really we feel reflects positively on ITI as a company. So many of you have been here before. This is the Showcase webinar series, which is a free monthly webinar that we put on to help educate and to really better the industry. You can see a number of our past Showcase webinar topics on the slide, and if anything there jumps out at you, all of those presentations are available to watch, the recordings, as well as the presentation files for download. So whenever you get a chance, something there interests you, like I said, you can access that by going to the Showcase webinar archive. So our host today is ITI President and Technical Director Mike Parnell. I'm sure many of you on the line are familiar with Mike's work in the industry. He plays a very key role on 2 American Society of Mechanical Engineers, or ASME, committees. And those committees help set the standards for lifting, rigging, lift planning. And Mike is actually the chair of the ASME P30 committee, which sets the standards for lift planning, and that should be released sometime in 2014. So one last thing before I turn it over to Mike. Everyone has a questions pane on their webinar dashboard. If you have any questions that come up during the webinar, please enter the question in there. I'll field those questions, and at the end of the presentation, we'll have a Q&A session, and I can get those to Mike, and we'll get answers for you. So I think that's enough out of me. I'm going to pass the screen over to Mike. So whenever you're ready, Mike, please take it away.
Okay, very good. Thanks very much, Jonah. I appreciate it. I'm going to pop my screen up here, and let's see if we get a good handoff. We've got let me ask you, Jonah, you're seeing winches and blocks up there. And I'll start show my screen.
Yep, you're good.
Are we good there?
Yes, sir.
Let's see. Okay. And I want to make sure, just let me know if we hit any bumps. Jonah, I'm going to put a new page, a little page up on this screen, just to let everybody know that you mentioned the P30. Everybody seeing that?
Yep.
Okay, excellent. Yeah, the P30 is scheduled to release. It's a new ASME document. There will be actually a short webinar on it. Mike Mills is a vice chair, I'm chair, and then Kate Hyam is a secretary for B30 and P30. Kate will be joining us. And let's see, the release date, if you'd please make a note of this, right now is scheduled, if all the printing happens accordingly, should be March 23rd, 2014. And then I believe we're looking to make a webinar on that. A couple of nice piece of information. Your webinar will be about, I believe it's April 10th or 11th, but we're going to send out an announcement to everybody that's registered on this program. And we're going to also then conduct a P30 lift planning workshop in Baltimore, and that's going to be in May, and I believe it's May 22nd, but we'll also send that out, and it's a 4-hour integrating the P30 into an actual lift plan development project, and that is also the week of the ASME B30 meeting in Baltimore, where we're inviting guests. And we'll send out announcements about that and registration opportunities for everybody that's online here and those that have registered. But we'll make sure that you have an opportunity if you'd like to attend that. It's going to be we'll have most of the P30 committee will be there, and it should be from, I think, 8 a.m. to 11:30 or so in the morning in Baltimore, and you get all the information as to where that is and so on. So it's going to be a terrific rollout for it. And we'd love to see you there. It'd be a terrific opportunity to see how it engages the document into a live planning project, and then for I believe we're using a 70-ton compressor installation project will be married up with that. I'd sure like to welcome everybody here. This is going to be a pretty fast-paced workshop. People have been asking me, Mike, when are you going to get back on the air? So, and do some interactive workshops, and this is one of those for 2014. We'll have a couple of more as we go along. We've had a number of guest presenters, and we really appreciate your attendance to those. Really super specialty subjects, as Jonah has identified. On the line with us today, we've got Advanced Crane Technologies. Brandon Strain, Randy's son, is new to the industry, but we look forward to having him work with us downstream in some activities. We have Al Faras is from the Middle East. Jimmy Chang is here with us, I think, and J.D. Barnett from BHP Billiton. And I think Ken Jacoby from BP up in Alaska is with us. We've got a bunch of folks from CB&I, Chicago Bridge and Iron, and Corps of Engineers, Navy Crane Center have logged on with us. Norbert, nice to have you with us from JB Driver up in Alberta. And Jim Worrell, I think you're on the line with LiftThink. Jim was a presenter, and we hope he'll be a presenter in the future with us. A super background in crane and rigging activities. Manitowoc Cranes is with us. Linkbelt is actually with us today too, and a number of other folks from Saudi Electric, Shaw Group in the U.S. here. I think we're still batting about 40 different U.S. states, 6 provinces, and somewhere about 20 countries around the world that has logged on to this presentation. So this is going to be fun. We're going to have a good time and get things rolling along. And let's open up. I hope a lot of you downloaded the link that was provided by Jonah for the workshops that we had. So we had about a 6 or 7 page document, PDF document that came out to everybody when you registered, and you got notification of it yesterday. And then also you had some rigging cards. I'll put those up on the screen. We're going to be working from a multi-panel rigging card. I'll just pop that up. And then we also journeyman card, and we also have a master rigger card we provided with the link. And so the PDF link document that we put up, this is the first one. This one really is about winches. It's keynoted as winch dragger roll, and so some of the workshops that we'll be going through today deal with those subjects. In this first example, we're just going to look at the one on the left for a minute on your page, and this should be on your page 3 of your document. But we'll just focus on this one for right now, and then we'll move over to the other one. We'll do a couple on static loads, frictionless system, because that means the world is perfect and nothing is hurting us from friction standpoint. And we may toss in some values. I'd like to go over a couple of things with you as friction builds in the system. We may do that on the first one here, and then we'll sort of keep rolling in a static mode. So here's the idea is that the load in this case, the load is 6 tons, and we've got a 5-part line. And for those that are new to multi-part systems, what we'd want to be doing is, an easy way to do that is to, and I'll blow this up just a little bit for a couple of minutes and we'll go back. So all we do is kind of put a knife blade going across all the lines that enter or exit the load. And how many lines we enter or exit as it's actually applied to that load or to that particular anchor point, that's the multi-part, lifting the load or pulling the load, and that is, sorry about that, and maybe I can get Jonathan in here in a minute and help me out, but the number of lines in this case, we have 5 parts of line against the 6 tons of load. And so the first question is, what's the load to the winch line? And let me back this out just a bit. And so we have 5 parts are reeved up, and we got the dead end right here on top of that block. And if you chase those lines up, I'll just kind of draw this flat for a second. It's up 1, 2, 3, 4, 5, down to our lead line. If you look up in a number of multi-part line books, you'll see lead line factor, lead line stress, lead line tension. It's always going to the winch. Or if we were in North Carolina, it'd be the winch, just for my friends back on the east there in the south. So we're looking for the capacity. We've got to ensure the capacity of the winch is going to be suitable, and it's going to work for us, and we're able to lift the load unimpeded. So let me get rid of this just for a second. And so we got a number of parts of line. So let's resolve the load to the winch line based on a mechanical advantage of 5. And I'm going to give you a second. We'll go ahead and do that calculation. And on the next page, we have, I've got the fill in the blank section. I'm working on kind of 2 PowerPoint frames per project. So one page will be the illustration, and the other is the fill in the blank for your questions. So let's go back to the illustration. I'm going to depend on you all to help keep our answers going on that fill in the blank page there. And I want to let's resolve the question. I've got 6 tons and divided by 5 parts of line, and so we're going to get 1.2 ton to the winch line. And each one, if I can make a little baby notation over here, 1.2 tons on this line, that one, this one going across, that one, and that one. So all those 1.2 times 5 gets us back up to our 6 tons. And so for static load, we have 1.2 ton is showing up at the winch. And so that'll be item 1A. Item 1B is our 1.2 ton. And then the question gets down to, well, what is the load at the main or big beam right up here at the top? What's that going to be imposed, and can we rig heavy enough to accommodate that? And I'm going to ask you some kind of surprise questions, and we'll get this cleared off on my screen here. And okay, thank you very much. Okay, so we're looking at the load, the downforce on the entire system is going to impose on that big beam up ahead. So that's the idea. So we want to evaluate, well, geez, what's it got? It's sort of acting like a crane. And this might be something very similar. You know, if I was able to draw in a crane boom right here, going up and encompassing that block on a mobile crane, boom cylinder and outriggers and so on. So it's sort of acting like a crane, and what would be on the head of that crane for load? So the idea there is, so let's resolve that because we set this whole winch system up and decide what we've got for downforce there. So we know we've got 6 tons, right? We know we got 6 tons. We know we've got 1.2 ton at least over here on that winch line. So we need to add those together, and our answer should be 7.2 tons right up here at the big beam. Now, I'll get into some other information real quick on dynamic load, but just for grins, let me ask you an off-the-wall question here. What size shackle do we need to put right in there to support that block? There's one up and one down. They're bow to bow right there. So what size shackles should those be? And let's open up that Journeyman Rigging card. And it says Journeyman Riggers reference card at the top. That's panel 1. Well, let's go down to panel 5. And on panel 5, we've got a whole host of rigging hardware options there. You'll notice in the size column is far left, and then we've got eye bolts, turnbuckles, master links, shackles, and so on. So let's look down the shackle column. What we had up there was 7.2 tons was load, and times 2,000, and that's going to give us 14,400 pounds. So let's find the first shackle that gives us that 14,000, and we're right there at 1 inch. So we're going to need at least a couple of 1-inch shackles, one up and one down. That'll connect that upper block to the big beam at the top there. And I think that probably will sustain us even for dynamic activity. So I'm going to swipe that away. So we got the shackles up there. If we were in a bigger workshop, we'd be working our way through and identifying all the rigging components, all the block sizes and so on, and taking care of that. Now, so we've got 1.2 ton at the winch, 7.2 ton up there at the top end. And for those, we're just going to do this one time. For those that are interested in understanding or computing the dynamic activity going on here, I'll just do a little off the side little review here. So I'm going to put the load on the first part of line. If you got nothing else to go on, here's the deal. If you got nothing else to go on, you don't have a lead line stress table, which can help do some of these computations faster. There is one in the wire up user's manual. There's one in the Boilermaker's handbook. There's one in the IPT red handbook. There's a lot of resources out there, lead line stress. Johnson Blocks has one, Crosby has one, and so on. So what we're really trying to figure out is lead line stress, tension to the lead line can increase as the friction increases at every sheave, and every time a rope goes around the sheave and tries to turn that sheave, it's going to get some additional resistance. In the simplest way, it's the most conservative approach, I'll go with that, is to start with our initial 1.2 ton, which is our dead end. That's our single line coming up here at the dead end. It goes over that first sheave, and as it turns that first sheave, so that's we're not going to. There's no additional friction on that single part, so that's basically times 1. But on the next one, on part 2, I'm just going to say part 2, and we're going to say 1.2 times 1.04, and what I'm using here is a 4% friction for each sheave as I turn. So 4%, I'm going to take 1.2 times 1.04, and we're going to get 1.248. So that is our second part of line, new tension. And it's really compound interest. For each part of line, We're going to account for that extra 4% of friction, and then we're going to add every single new part of the line all the way to the winch. So we'll take that 1.248 times 1.04 for the third part of the line, and we're going to get 1.298. So that's P3. P4 is 1.350 is part 4. I'm going to just write all over the page here. 1.404 is part 5. And down to the winch line, I'm going to do that one more time. 1.460 is W, or winch line, WL, we'll call it that. So if I add those values up, really, while the thing's turning and hoisting, I'm going to identify that that's really my load to the big beam. So really, instead of 7.2, we might be at 8.5 ton. We could be up to, I've got, I think I added it all up, and I've got a total load up there right now of 7.92 ton instead of 7.2 ton dynamic. So we're still good for 8.5 ton shackle or 1 inch shackle, but just realize dynamically we're going to be creeping up in the overall anchorage loading, and certainly in the overall winch loading that happens down here at the tugger or at the winch. So that's the only time we're going to do that. There's dynamic and static. Static's non-moving, dynamic is moving, and as we continue to impose value, impose and hoist, we're going to see that dynamic number go up. So we're at 7.96. Sorry about that. 7.96 ton dynamic and 7.2 static. So there we go. All right, so the rest of the workshops we're going to deal with will just be static. And let's go over here to number 2 on the right side. And so let's take a look. We've got a 4-ton load, and we're actually supporting it by 2 different support points up above. One is a low beam, one's a high beam, named for obvious reasons. And we want to see what we're going to get in a variety of locations. The first one on your page, on page 3, is what is the loading at the winch? And so let's see, we're going to use that same process again. So work through it, see how many arms are lifting that 4-ton load, and if we put that knife right across there and bisect all those hoisting lines, we're going to find that we have a mechanical advantage of 4 in this case. So we can count then that each part of line in static condition has got 1 ton. And so sometimes if I'm doing a quick estimation, back that one out, I'm just going to do a 1, 1, 1, 1, and then guess what? 1 right there. Because this 1 on this winch line has got to pull the brother right behind it. So yes, it's going to be more because of dynamics, but we're getting the whole general gist here. So we have 1 ton plus friction. I'll just put a plus F down there for the winch line. Then our next question, I'll get rid of some of these other things here, kind of get them out of our way here for a second. So the next one is, what's the question is, what is the loading at the high beam? What is the loading right up here? So really, if you just mark your page with those values per part of line, it's the easiest way to arrive at the approximate value up at that high beam. And I had 1 ton on this line and 1 ton on that line. So really, I've got 2 tons on the high beam. What is the load value for the low beam? And if we just follow those lines up, there's that one, this one, and this one. So I got 3 of those. So I've got 3 tons up on that low beam. So if I go to my answer page, and I'll put this up on the screen, most of you have this, have your fill in the blank items here. Let's just update this. So we've got, this one was B, this one was A, 7.2, this one is C Charlie, this one is on the high beam was 2 tons, and this one on the low beam, C Charlie, is 3 tons. Excellent. Okay, Great job, Will. We're just going to kind of keep rolling here. We've got another workshop. This is sort of interactive. If you're working ahead or we're kind of working together, that's all good. Whatever works for you works for me. So on this next one on page 4, we have 4 different examples of load moving, skidding, and in that regard, so we're just pulling this puppy sideways. So this is part of the winch drag and roll approach for dragging, and it does happen. We just got to skid it, slide it, move it. But we've got different values that are going to throw us high and low for the amount of force required to move those loads across those surfaces. So what I'm going to ask you to do is to take a look. I think probably the most advanced card you can get in front of you right now is listed or tabled as the MRRC, and that's the Master Riggers Reference Card. And I'd like for you to go to panel 6, and that's the 6th page or 6th panel. And let's take a look at this guy. And we, at the bottom end down there, you'll notice this is kind of a, and we'll be using this formula later on, but this is got a series of coefficients of friction that are listed down below on the bottom part of that panel. And notice we've got a variety of materials there. Now, when we put these on the card, I want you to know, and for the engineers online with us here, these values really, let's just take one for example of wood, and you'll see that it's got a value of 50%. So in strength materials engineering books, a number of tests have been done, and what we'll see in some of those books is wood on wood. Get rid of this for a second. Wood on wood, and we have a range, and the range may be from 70% to 30%, depending on the whether it's sanded or not. Rough, sanded, rough. We may have hardwood, softwood, wet. I mean, just all kinds of conditions that can enter into that. But the average, the breakaway average for the two materials, on a flat surface of wood surface and a wood block to sit on it, the average breakaway will occur, and these are kind of at slope or grade, at a between 30% grade, 70% grade. That really equates to the value that we use for the coefficient of friction. At what point will this wooden block surface down here break away from the subsurface? So what we've done is we've taken the average of those values that we all find in those books and done some testing ourselves, and what we found, we've taken the average number of 50%, and that's what you end up with on your card. So I'm going to pull the card back up and note that that average number that you see on that card is 50%, and that is the mid-range number that comes in from a variety of testing. Some will be higher, some will be lower, but that gives us a starting point. We all can see that concrete on concrete is pretty high. It's here at 65%, and it is a that can vary maybe from 80% somewhere down to maybe 50% or 55%. So the value that we have is the average of those numbers. Just as a byline here, we don't put it on the card, but I can tell you aluminum to aluminum is somewhere in the 1.50 range. It's extremely high. You have two aluminum surfaces. You got aluminum deck in the bed of a truck. You got an aluminum gearbox in the bed of the truck. It takes more to slide it than it actually weighs by 50%. I mean, it's huge. The atomic bonding between the two materials is huge and very high friction. So it's just, we didn't put it on the card. You don't see a lot of that happening. And you slide it far enough, quick enough, you're going to melt and you're going to weld it together. So didn't think there was much future for labeling that and listing that on the card. But it just gives you an idea that, gee, that's a huge value, and it's just the atomic bonding is really alert and working right there. So we're going to use these values. Let's use these values, and notice on the card in the upper right-hand corner that we're lifting or we're pulling and dragging on a level surface. And what that, on the legend, what we're instructed to do is to take the CF, coefficient of friction, times the weight equals the force required to move that load. So we're going to use that formula to solve page 4 in our book here, in our handout. So remember, I'll just put the formula back here, CF times W equals force to move that load. So let's find the value, the coefficient of friction for each one of these, A, B, C, and D, and let's apply that formula to each of the 4 cases that are on the screen. And you've got page 4 in front of you. Go ahead and work that out. A lot of you have already, and we're just going to kind of be working right behind you here. So we've got a value then, our load's constant. We just put different materials underneath it and a different surface for it to bear against. And so in the first case, we've got the load's 12,000 pounds. W is going to be constant throughout this workshop portion. So the secret here is concrete to concrete. So that's going to be what? That'll be 65% times 12,000, and we're going to get a value of approximately 7,800 pounds for that first example. So that'll be A, 7,800 pounds. The next one, we've got wood on steel. That one will be 0.30 times 12,000, and that's going to give us 3,600 approximate force to move that load across that floor. Let's do the next 2 down below. A lot of you are working right ahead and keeping moving with me. So we've got the next one is steel to steel, very light coefficient of friction, generally 10% times 12,000, and that's going to be 1,200 pounds of horizontal force, more or less, to get that load going. And the last one, we've got wood on wood. Remember that from our first introduction. So we've got a 50% coefficient of friction times 12,000, and we're about then 6,000 pounds to move that load this way. It might cost, it might be, really, it could be 5,000, no problem. Breakaway might be a little higher. That's okay too. We're going to have to kind of figure, you might anticipate 10 to 15% extra, 20% extra for breakaway, and then once it's sliding, it goes easier. We can reduce that friction all the time by putting lighter, lower atomic bonding type materials in there. UHMW, grease, soap works well on a surface. So there's a whole lot of ways to lower the friction. In some cases, you want the friction to work for you. So increasing and decreasing it is always a big help. Now, let's take a look. Let's go forward. We're going to combine those 2 workshops into another workshop. So let's take a look. Oh, I want to make sure. Let's transfer our numbers over to our page here. So we've got that. I just want to make sure that we're dotting the I's and crossing the T's here. So I've got 7,800 there, 3,600 there, and we've got 1,200 here, and we've got 6,000 there. So that's on our answering system here for all those that are following along. Okay, now we've got the next page. I've got page 5 in the handout that you have in front of you. Well, we've got kind of a complicated system going on here, but this isn't unusual. I've been in a Ford plant, a couple of other locations where they've got a winch set up in one location, and that winch is dedicated to that location, and from there they take off with a variety of blocks. We've got them just rigged around columns right now, but they've got floor blocks, ceiling blocks. They can reroute that winch line within 2 or 3 adjoining rooms to do conveyor system transfer, plate transfers out, and so on, machinery and equipment change out. So they'll use one winch in a central location and then work it in 3 or 4 rooms by rerouting it with different diversion blocks. So in all those points, if we free rig it, meaning we walk in, say, okay, I want to put a block over here and there, we're going to need to check with the building engineer to make sure that column, that beam, wherever we're going to anchor to, that's got sustainability. It's got the it's robust enough to take the loading that we're going to see when we start moving that object. Now in this case, we're looking down on this load. It's a 100-ton press. So that guy's right down here. And what we're doing is we're moving this press forward. I'll just make some initial drawings here. So we're moving this press forward on rollers to that little X box right there, X square. And so that's the idea. And we know that the load weighs, we're told that the load itself weighs 100 tons. And so let's go back to our rigging card. That master rigger card would be very helpful. Notice you've got a load on wheels. So we'll take a look at that load on wheels right over here on that right side. And I'll kind of highlight that. We'll get rid of a bunch of this other stuff. Highlight that. And I do have something to share with you here that's kind of an aside. So we've got a load on wheels here. It's about 5%. We can set up a series of rollers that can help move that a little lighter. I toss up on the screen here for you. Just take 5 with me. We certainly do a ton of jacking and rolling instruction. I just pulled some documents up here quickly. I've got 3 little pictures. We have an incline ramp at all of our training centers, bringing a load right up the incline, and then up onto a flat surface. So we have incline plane calculations, winches, tuggers, and so on. But I wanted to show you, this is a 3-point system right here, and that is a steerman. That's just a trade name. That's got a steering end, and then we've got 2 pup ends. And I think I wanted to share with you as well. There's a let's see, we've got for our 0.5 here, let me take a look at that with you. Don't worry about the, we have some transition. So, but take a look when we're moving loads sideways, we've got to be really careful. I'm not going to draw all over this, but notice we got a load going up an incline here. Load weight, center of gravity, what subsurface dictates the system we're going to use. Is it incline or level? What's the floor surface look like? Wheels, pipes, skid, air casters. We got a new hydro slide system up in Edmonton, 400-ton unit up there we're using for master rigger courses. Notice down here in the page we got pipes that we actually roll loads. I mean, we get back to caveman rigging just to help teach and ingratiate the principles to the participants. So we use wood rollers, steel pipe, Hillman rollers, steel Hillman rollers, multi-ton, steerman, synthetic wheels, air casters, and so on. So we want to just always take these things slow. We always got to watch out for where our center of gravity is for stability. Make sure that our support points are ahead and behind, and we're side to side, and we're supporting the load properly there. Just kind of hobbing through this, but just something to kind of share with you. When we're jacking loads, by the way, too, one end or one side at a time, we'd never jack a load on 4 mechanical jacks on 4 corners at the same time. Really dangerous practice. We can helicopter that thing down pretty fast and crush a foot or hurt somebody pretty bad. We chase blocking up and down and don't get more than 4% grade out of level. So we don't want to side load the jack by getting too aggressive and trying to raise one end too high or lower it too much. We want to chase that up and down with blocking. So guys using jacks here, synchronize, keep hands and feet clear, and ensure that the jack to CG location is good to prevent overload to either the roller set system we're about to place or the jacks. This is that 3-point system that we can use, and we have a number of sets of these. This is, excuse me, I think this one is the 5-ton unit. We got a 25-ton unit to come bigger. But notice that we got a steering end at one end and 2 pups at the other end. On this right-hand picture, we've got the 2 pups. They got a crossbar there to keep them square and true. They only go straight, but the steering end makes a rotation, so you can steer and literally drive this thing around in a 360 from the steering end, pivoting on one corner right here to help make that turn. So it's a really handy system. one thing you always want to make sure of, because we're going into a workshop on this moving a load on wheels, is to make sure that center of gravity is contained and within that triangle support. So you've got a steering in, a pup in to the south, pup in to the north, and on the far east side there you've got your steering unit. And if this center of gravity was further to the right, that'd be pretty dangerous. Stability could be an issue. In that case, we'd want to flip the whole system around. So you want to have that center of gravity, you know, at midline or closer to your double pup in down there. Keep it as far away from your tipping axis as possible, as reasonably achievable, and watch out for the height of the center of gravity. In the z-axis, X, Y, and Z, we always want to make sure vertically that the center of gravity is contained and stable. So we have to push our footprint out. We have to put outriggers on underneath the load, you might say. Put some beam extensions out that create better stability. You know, this really is just working on the same principle as a pallet jack. Nothing new, but 3 points roll is a great system versus 4 point. We can kind of go into that later on another workshop webinar. But really, you got a single down here that steers. You got a pup there and a pup here, and we're containing the center of gravity. So it really is the same thing, not new thinking. We're just reapplying it in different ways. So let's go back to our, oh, by the way, and we do have an air caster system. In this case, we've got 4 air casters. And because we can actually adjust their elevation by air pressure, then you can use 4 on the load like that. There's 2 on the front, 2 in the back. These guys are bringing a load back into a building, and they're having to actually go over an obstruction. So pretty challenging move there, but they're getting it done. So we've got a variety of ways to move loads. I'll close this out here and say no to that. So we're going to move a load on wheels, and we said about 5%. On synthetic wheels, I can tell you, our experience has been about 2.5%, somewhere to 3%. Coefficient of friction, nice big wheels, good roller bearings, standard wheels, nothing to hurt to go 3 to 5%. So that's what we're going to use for the workshop. So let's go back to our page 5 there in the book. And the first thing we want to do is arrive at, you know, its dead load is 100 tons. And what will be the force required to move that 100 ton on wheels? So using our previous workshop, I'll just write across the screen here. If you remember, we'll take the coefficient of friction times W equals force. So in this case, our coefficient of friction is 0.05 times the load of 100 ton. It's going to give us 5 tons to move that load to the north, if we call that north. So get rid of that for a minute. So we got 5 tons anticipated to get that puppy moving. And let's see, so I've got 5 tons. And that's my magic number right there. And on my answer side, which is where everybody, we can be recording our information here. So our first answer, weight's 100 tons, sitting on industrial rollers. What's the anticipated force? And that force is 5 tons. That's going to be B. Now we've got a whole variety of questions at various connection points, columns, and winch to see where we're at for anticipated load. Now let's go back to our drawing. I'll just put that up on the screen here. Hope everybody downloaded their link. I mean, otherwise you're kind of working off my screen, which is a poor substitute. So I hope you got your workshop and your cards with you. So what we want to do, remember what we did last time, we want to kind of find these values. I mean, we're going to be searching for load at column T, S, R, Q, and what's the load at the winch. That's the North Carolina version. So we want to see what we have for load at those. And remember, we just talked about cutting the hoist lines or winch lines that are entering or exiting the load. In this case, there are 4 of them. So we're going to take that 5 tons, divide by 4 parts of line, and we're going to find out what? Our line pull is going to be 1.25 tons per part of line. So I just do this 1, 2, 3, 4. So each one of those has got 1.25, and I'm just going to write 1.25 tons back here at the winch. Now, for those of you that were chasing the dynamic value, I did a little pre-work and just adding 4% for every part of line after the first part. And that 1.25, so if I put that, just put an S there, I'm going to put down a D number for dynamic, and I arrived at 1.65 ton. We won't do any more of that, but I just wanted to let you know. So dynamic for turning all those shifts, not breakaways not really counted yet into that, but about 1.65 ton on the winch. A 2-ton winch minimum would certainly be advisable in this case, and higher would be better. But so 1.25 ton is our working number. That's what we'll use for the balance of this presentation. So let me get rid of a couple of things here. That's good. All right, excellent. So a first question, we can, if we're going to use 1.25 tons, the way the questions are set up on the book, or in the, we're kind of working backwards from the winch back to, so that winch is 1.25 tons, and it kind of goes backwards, Q, R, S, T, and we're going to work back to the load. So those are things that we're going to, our next discovery points are going to be, we're going to go right back here to Q, and I've got about I got a 135 degree included angle right there. So geez, what's that do for load to that column and that block and sling and shackle that are holding that block in place? So we got now. So just kind of note in our heads, we've got 135 degrees. Now I'll take you to the first. Let's take you to a card, the Journeyman Rigging card. It says JRRC. Let's go there, and let's go to panel 4, and you have a living example there on panel 4. And we've just stuck in here, just for educational purposes, we just put in line pull of 6,000, load of 6,000, and then gave a variety of block setups at 180 degrees, 150, 120, 90, 60, and 0. So we set this up as an example to the right. The example certainly follows out over here in this column, line pull, and follows to block loading. But of special importance here, I want you to take a look with me at the formula. And the formula says that we want to take the block factor times line pull equals block loading. And block loading will dictate what we use for backup slings to restrain or hold that block in place against the column. Now you'll notice, I take you to this, so let's just work this one at 90 degrees. I know we're going to have one of these, I think, in the workshop. So at this 90 degree setup right here, what we're told to do is take the block factor. In this case, we're going to read right across there to 90 degrees, 1.41, in this case 6,000, and it's going to result in a block load of 8460. So we'll take block factor times line pull equals block load. All right? Okay, and that's pretty straightforward. We're not adding dynamic winch line pulling right now. It's all static, so just to kind of get us there. Now what I want to do is take you to, now switch cards with me. I appreciate everybody being so easygoing. I don't hear you screaming or gnashing of teeth or anything, so that's good. So let's go to the MRRC, Master Riggers Reference Card, Panel 1. Reduce this just a little bit. So I'm right on Panel 1/2, and you'll notice you got a whole bunch of values right there in the big table, a whole bunch of columns. What I want you to do is to go over here with me to the full included column right over here. You'll see that that full included column, and it goes from 0 to 180, and it goes in 10-degree increments. And then the column right next to it is the block load factor column, and those two columns really work together. We packed these are actually rigging cards that we use for all of our training programs. What we just did today was to give them to you in PDF form. These two, the value we had from that first block. and that block value, let's see, let me get this highlighted here. That block value at Q is 135 degrees. That's the angle, as if we'll include an angle. So we're going to search that card out, and let's see where that puppy comes in here. So I've got a 130 option and a 140 option, and my diagram is showing me 135. So just like operating cranes, we always go to the one that, in that case, that would produce the lowest gross capacity or lowest capacity for a crane. We would find that on a load chart. In this case, for rigging, same concept is which one would produce the highest block load. So at 130 degrees, I see a block load factor of 80.84, and for 140, I see a block factor of 0.68. So between those two, which one was going to produce the higher block load result for me, just using those two as the options? And if we picked 0.84, that would be right. We're going to use that higher one. We know it's a little higher than it might be at the 135. We're not going to interpolate into this thing, but we're going to just pick the 0.84, and we're going to use that for solving our problem. So right off to here, I'm going to get rid of some of this, a lot of this scratch up now. We know our value is 125. Let me get rid of that. I appreciate everybody's patience. I'm just an old man having fun here. So, all right. So, got a 0.84 times line pull. So that's block factor times line pull, LP. And so we're gonna put in the value for line pull right there is 1.25, and that's going to give us what? It's going to lower it, isn't it? Right? So it's going to be 1.04 tons. So as we open that angle up, we're going to get less and less and less load to the block. If that line was running right through the block, it'd be zero. There's no load to the block. It's just a fairly kind of hanging out there doing nothing. So as we make that angle at 120 degrees, that's going to become, that 120 would be 1. So as it gets closer and closer back and it closes up to 0 degrees, then our load factor, block factor is going to be 2. We all know that. I think you guys saw that on the card. So we've got a value right there of 1.05 tons should be the answer for Q. 1.05 should be Q. Let me give you a minute here or so. Let's work out what is it going to be at R, S, and we're going to work together on T. So I'm going to kind of quietly work my way over to the card again. I'm going to see what's my next angle. 45 degrees. That line comes in and out at 45 degree full included angle right there. I'm going to kind of quietly go over to my card, take a look at my card and see, well, what do I have in the 45 degree department? And let's see what we got there. So we're at 45. I've got 40 there and 50 there. So I can see I've got 1.87 and 1.81. So I'm going to use what, the lower one or the higher one? Excellent choice. We're going to use the higher one. Very good. Excellent. All right. So we're going to use 1.87. That's block factor times line pull of 1.25, and that value, we're going to put that value down here as should be 2.34 tons on R. Okay, 2.34 tons at R. Excellent. Okay. This one you'll know in your sleep because it works in a whole lot of rigging stuff we do for everything else. So let's go up to S. We'll go find our block factor at 90 degrees. So we'll go down here, 90 degrees. Our block factor is 1.4. 1.41. We'll use that. Solve this little puppy out here. So my block factor is 1.41 times line pull of 125. And my block load is going to be 1.76 tons. Okay. So, and why I find that block loading, I need to get a sling that'll go around that column and protect the sling. I got to get approval from the building engineer. Can I put, like down here below, can I put almost 2.5 tons down there on that column? Can I put almost 2 tons up on that column pulling on it? Will my anchor bolts work? You know, so it's a whole lot more than just the rigging. We've got to confirm the building can still stand up after we get done with the job and so on, because we're going to put so much load to it. And we're going to put an awesome amount of load against column T over there, because we got a whole bunch of lines and force going in or pulling out from that column, not all in the same direction either. So my goodness, we're going to be inducing a ton of pull against that thing. So now we've got Q, R, and S. We've got those. Now we're going to work on T. So I'm going to kind of wipe all this other stuff out and get so we can take that page up. Let me kind of bounce this page up a little bit. Get this into view. Sorry about that. All right. So we're going to work on T right here. So kind of a simple way to look at this, and I say simple because that's the only way I work, is I start out like this. I know I've got 3 straightaway pulling lines, 1, 2, and 3 from right to left there, that are going to show up at 1.25 each. Now this 4th line, this guy is going to go up, go into that block, and go to our left. And he's working at a 90-degree block, so that's going to result in something unique, kind of pulling this way on that column, because mothers are pulling due south if we put it in that direction. But that's still a load. It's still a force being pulled against that column base. All that rigging's going around there. Just got to make sure we account for it, and can we take it to the building engineer and get his approval. So if we remember, we're going to use that, remember the block factor times line pull equals block load. That's our formula. So in this case, what was the block factor for 90? Excellent. We remember that. That was 1.41 times line pull of 1.25, and that gave us a block load of 1.76. So I'm going to take this little puppy and go right over here with it and add them to these 3. And at the end of the day, those combined are going to make 5.51 ton of force pulling against that column. Now what we all appreciate is that it's not all in the same direction, but we have just slightly over 5.5 tons, and you know, we can sit down and arrive at the exact final vector for that column, and you know, it may be down in, you know, let's just going to draw a line here. It may be down in that range. That's the final vector, you know, potentially for this guy. Excuse me. So, but we want to take this number 1. Can we rig up everything accordingly? Can we get the right block sizes and shackles? Can we get the right dead-end connections for slings? Can we rig the slings up to it, protect the slings and so on, and account for the block or the final load to that column and get the write-off or sign-off from the engineer that we've got that accounted for? So that's the whole idea is, my goodness, we're piling a bunch of, but you know, it shouldn't be a big shock when we step back to the big picture here for a second. Let's put this into view here. Shouldn't be a big shock. We've got a whole bunch of, you know, our initial project was to pull this puppy forward and move that forward, and we know it's already 5 tons of rolling weight, or rolling force to move that. 5 tons to move it. So the fact that we ended up at 5.5 ton load at that column, I'd say we got off pretty lucky, actually. You know, about the worst things so that we could do for this, here would be kind of the bad idea of the day, would be to somehow arrange our winch system to cut a big honking hole right through the walls here and take this and try to do this with it. Now watch what we're going to do. We're going to come off of this block right here, and I know the block isn't sitting in the perfect position. We're going to run right through those walls and put a BA block. That's a BA block, and then in Missouri where I grew up, that's called a big-ass block, just so you know. We're going to put a BA block right there, and we're going to come down and put a big connection right there to the load. Now, my goodness sakes, what do we got here? So if we took, we might call that angle right in there. Let's call that 20 degrees. And I know what I got, 5 tons there. Let's go to our rigging card for the master rigger card and see what 20 degrees is for a block factor force. Oh my goodness, look at that. So 20 degree included. My block factor right there is 1.97. Isn't that, man, I don't know how much. I got to get my calculator out for this. So let's take a look then, 1.97. Wow. So I'm going to take, let's 1.97 times our 5 tons. Get that going in here, 1.97 and 5. Oh my goodness, we got 9.85 ton on that column right there. So that's the part of the beauty of mechanical advantage. Adding parts to lines reduces the amount of force, and every block you want to put into that system, either mechanical or diverting blocks, it can always kind of help reduce those anchorage points, because if we want to just go straight into that column and right back to the load and just try to give it a monster pull, you know, we're going to actually put massive load. You know, this block's going to be reoriented, you know, kind of over here, but we're going to put that same honking load right down here. So we're going to put 9.5 ton to that and 9.85 ton to that column. I mean, they're about the same angle, so my goodness, we're going to put almost 10 tons to a column. There's no reason to do that. That's why we buy smaller blocks, get a nice small, good high-capacity tugger, and multi-part that system and reduce that line pull, reduce the respective loading to those anchorage points. Because just doing a single line pull, oh my gosh, that's huge. So anytime we can multi-part, we're saving our bacon and lowering that load to those anchorages. Okay, so let's take a look then, and let's double check our answer section. I don't want to leave anybody hanging. Everybody's we're all working from the answer stuff, so I'm going to replicate our answers from the other page. This one should be B, 1.05. R is C Charlie. That was 2.34. Item 5 is A, and item 6 is B. Excellent. Okay, very good. So let's go to take a quick breath. Okay, we're ready. So let's take a look then at pulling a load uphill. And of course we wouldn't want to put rollers on it. That's too honking easy. So we're going to skid this guy up there. We got a BA dozer up there. And you can feel free to go ahead and mark your page there. You know what BA stands for. So we got a BA dozer up there with a winch line, and we're going to skid this guy right up the incline. And it's 12,000 pounds load, and significant information right here. It's on a wood skid base, and it's on a concrete ramp. So this concrete ramp is there and here and there, and so we're going to slide that puppy right up there. And this is part of that winch dragger roll. So right now we're in the dragging business, and we're going to see what we're going to get for resistance. What amount of force is required to get that guy to go up that ramp? Now there's one piece of information here that we need to get started with. And so let's look at our fill in the blank information down below. I'll get over to the next page there. So we know what our weight value is. What is the coefficient of friction for, let's see, we've got wood on concrete, and where can I find that? Let's take a look. Let's go back to our master rigger card, panel 6. That's the master rigger card, panel 6. And our average value for that guy, you can all kind of see that down here. Our average value is showing up, wood on concrete, and that looks like 45%. Okay, at 45%, that's our, so when we do our little formula, it's going to be 45% CF times W equals force. But look what's going to happen here. We're going to get a new special formula. So stay on that panel 6 with me for a minute. And we have 3 total formulas in the upper right-hand corner. One is working on level, one is going uphill, and one is moving downhill. So we're going to use this uphill formula and incorporate that into this workshop. You're going to want to get that page and that page 6, panel 6, to be able to work the workshop page 8. So let's get that formula right there. And we're missing some. So and let's understand what we have over here for the legend. And this says in the formula, this says coefficient of friction times the weight times R, which is run, horizontal run, divided by length of ramp. That's our incline, plus height, vertical height, again divided by length of ramp times W, which is weight, equals the force. So let's take that formula with us over to solve this problem. And we know our CF, coefficient of friction, is 0.45. Excellent. Okay, so let's see where we're at here. We got that, so let's go to that page. Okay, so our run, based on our drawing, we have that at 10 feet. And our height, based on our drawing, is 4 feet. What we just don't have yet is length of ramp. So I'll put the drawing up. We just identified, we just found out the run is 10, height is 4. I just don't have that length of ramp based on that. And what I need to do then is figure out, well, that's going to take me back to the Pythagorean theorem, and let's get, so if we remember, we've got, let's just apply here, a squared plus, around this corner, b squared equals our unknown length of ramp, c squared. Okay? All right, so let's just do that while we're here for a minute. So we've got 4 squared plus 10 squared equals our unknown c squared. And we know we've got that's 16. 4 times 4 plus 10 times 10 is 100 equals c squared. We take 16 and 100 is 116 equals c squared. And I'd get rid of those by squaring both sides. So this square root on the right takes away that guy, so C equals, and let's get that down, and I got 10.77 equals C. All right? So that's 10.77 feet. So let me get rid of that stuff. We haven't fun yet. That's the important part. So I've got 10.77 feet for that length of ramp right there. Now I can put that on my next page. Now I've got that 10.77 feet. All right, so the question is, the big question on this, looking for the solution here is, what in the heck is that winch tension during the incline movement pulling that uphill? That's what we want to solve. So let's put that formula up on the page, and what I'm going to do is I'm going to slap a new kind of a new page up here. Well, I can work from this, I think. I could do that. Increase this a little bit. All right, let's try this. Give this a whirl. Okay. You know, I'm going to run out of space. Rethink. Let's do this. All right, let's put it up there. So we've got our formula, CF. I'm going to replicate that formula, times W times run divided by length of ramp plus, let's see, height divided by length of ramp times W again equals force. So let's put in all the little things that we know. So I've got a 0.45 times 12,000 times 10 divided by 10.77, and I kind of got to work all that out on the left side, plus, let's work this out, I got 4 divided by 10.77 times 12,000 equals my force again. So just sort of work the left side and the right side, and let's get down and add them together. Let's give you a chance to move right ahead with it. We're doing pretty good for our time on our workshop. We're trying to schedule for about an hour and a half today, and I got two really cool final ones. We may just do one at the very end here, but something we did for one of our clients. It was really neat. So while you guys are working that out, let's see what we got here. So let's see if we got to the same place. I got 5,400 times 0.93 plus, I got 0.37. Let's see if we agree with this, times 12,000. F, I got 5,022 plus 4,440 equals F, and I've got 9462, more or less. 9462 is what I come up with for our value for force to move that uphill. Yes, there's some breakaway, and it can kind of float up and down, dynamics and all that, moving and skidding and working, and so we're going to transfer that. Let's take that right over. So I've got about 9462 to pull that puppy up the hill. If I look at my winch on my dozer, I might be asking, you know, do we have a 10,000 pound or 12,000 pound capacity winch? And how good's the dozer for staying up on top of that little hill up there? I mean, there may be all kinds of opportunity to see if that's going to work as our anchorage points and so on. So he may actually, and we've seen this, saw this on a grooming project for a highway embankment, and where a guy would run his winch line down, come down, and then to help pull another dozer back up the hill as he's working in grooming, he'd run over and anchor off to a third dozer working on the side over here. So run a block here, so they can split the load to some degree, and it certainly gets higher as he gets higher, so they get really close together. But to help pull this guy back up and down the hill to work it that way, so put a block there and so on. So we just got a straight line pull, and we should be looking at 94. I'm just so excited. Most of you have been with me before on these, and you know, I just kind of wander off into these little bunny trails, and I appreciate your patience with me. I just have a ball doing these, and I really appreciate a lot of you coming back for the second, third, and fifth, and 16th time. So we're just having a blast here. So 9462 is our anticipated tension there. So let's just take a look at one of these let me put them up on the screen here for us. I'll back this down a little bit. What got us into this, and we'll just do this one, I think, and we'll call it good. We just don't want to run too far over time here. But what we did was, with the client, they're working in an underground vault, and so you got to kind of envision here. They got a hatch. And this big vault is this is an underground vault, so this is all underground, and the big where these guys are working, it's an energized vault, and this wall here is all working that way, and they got conductor that runs underground, and in this location, 85% of their power is all underground power in this particular city. So they've got a ton of underground wire running all over creation, and sometimes the wire burns up, things happen, and they get stuck, and they may have a 400, 600,000 foot run of it or more, and big wire, and it gets burned up and sticks and in the conduit. I mean, just ugly things can happen. So they've got to pull this wire out and replace it. So breaking it free is most generally the biggest challenge, and we're working with them using dynamometers, big winches, you know, just trying to anticipate, know what your load is, what the load is, and understand what the anticipated resistance is going to be, and then try to rig up for it. So it's a lot of work, and it's really dangerous. I've been down in vaults with these guys working and pulling and energized stuff around in some cases, and oh my goodness, it can get just a little dicey. You just don't want to fall over and grab anything and get all lit up. So so we worked with them. We designed some floor plates, and their engineers stamped off on it, but these are 5,000-pound capacity floor plates, and what they are is they're plate like this. I think they're 5/8 plates. They've got a solid round stock that's welded right here, and then they've got a hole, and let's see. That hole is drilled and tapped for a swivel hoist string of the appropriate size for 5,000 pounds. So that's what you're seeing here is the bale. It's all torqued, and then these are all anchored, four-bolt anchors that are setting this thing in place. So that's what. So to help give them, because inside a concrete vault you got really no rigging points. You got to build your own rigging points, anchorage points. And then we worked with them on designing or developing high-strength short slings that can kind of go up, and then using with roller blocks that'll adjust back and forth as the angle changes. You've got to have the latitude to be able to roll back and forth here, roll back and forth there, and as this block may change its position or something's working in and out of it, you've got to be able to have the freedom. It's just really like tilt wall construction. So share that load out, distribute it out, and penny the thing down to lowest possible reasonable value down onto the floor. So thank you all for staying with me there for a minute, but that's kind of what this is all about. This is really tough, dangerous, tight confines rigging activity, and we needed to come up with good solutions, and this is where we're dialed in with them. So let's, you can see on the page there that the value is 4,500 for the dynamometer that's showing that load being pulled out, and we certainly want to make sure that's anticipated, that is what that broke free at, and then of course it reduces as you continue to pull it. Once it gets free, then you just we have a way to pull that wire up and out of that hatch cover and free it up and roll it out of there pretty quick. Here's the question. What is this? So we needed to know what's the loading at block A, and so we have questions on our page based on the 4,500 pounds, basically line pull, we can already note in here 4,500 pounds for D because that's line pull. So that's a given right there. We know it's a little more for dynamics and friction, turning that sheave and so on. But so we're going to put D, 4,500 pounds for line pull going up to the winch. Now, here's the question, what is the loading at this block, A? What's the loading at the baby block, B? What's the loading at the floor plate, C? So now we kind of got to start breaking that down and see what we got for paying out and redistributing that load down to those smaller blocks. So I'm going to increase the size of our drawing here, bring this up into view, get rid of some of these things here. All right, having a ball, having a blast. All right, so we know that we've got a line pull. So what I need to do is go back to my block factor column on panel 4 for my card. I can see I've got a 60-degree angle right there, and the line's coming straight in here, going around that block and right up to the winch. Okay, so I'm going to go back to my master rigger card panel 4, or I'm sorry, panel 1, and I need to find the block loading for 60 degrees. So let's find what that guy is. So block loading, I'll come down here and find out at 60 degrees. My block loading, my block factor is going to be 1.73. All right, awesome. So let's go into our diagram. So we're going to take, remember, it's block factor times line pull equals block loading. So we know that our block factor is 1.73 times a line pull of 4,500 equals a block load of about 7,785. I know a lot of you are crunching numbers and pushing that in, and we're just kind of walking and talking together with this. So block loading at A is about 7785. So that's at this block right here. Well, funny that it looks, but we got a shackle right behind it, and another shackle going into that, and another block right there. And that load is transmitted right to that block. So our 7785 that shows up at the lead block right here is transmitted in a straight line right to that receiving block on the far side that's trying to help equalize down to those floor plates. So we're going to just write that in here, 7785 pounds is block loading at A. Let me get rid of some of this stuff now. And what's going to happen here, we're going to have a block load of 7785 there, and we're just going to, that's going to be divided by 2 arms, you might say. We're going to transmit that down to 2 sub-blocks or baby blocks. And it's so close to 0, we'll just call it 0, and the simple thing to do right there is what? Let's just cut this guy in half, divided by 2. And that's going to give us 3893 per block. So this block on this side is 3893, and its twin brother right over there, 3893. So I'm going to use that. I'm going to put this in 3893 right there. So we're going to take that down. So we've got 3893. And we're going to break that block's load down one more step. And the picture doesn't look like it's 0, but, you know, believe me, it's a Wednesday. It's okay, no problem. So we're going to break that block load down by 2, because that's the worst load anyway, you know, best condition. Well, let me back that up a bit. If this gets wide, here, let's get the value first, and then we'll just do that. So if you keep the numbers on your calculator, let's take 3 893 divided by 2, and we're going to get 1946 or 47, depending on your rounding. And that's our anchor at the anchor plate, and hoist string is 1947. I think you got 1946 on your sheet there, but it's just a rounding issue from the first calculations as we step down. So let's solve this. Let's put these values over on our answer page. You guys are doing great, hanging right in there with me. Okay, so we've got, we know that we've got block load at A is number 4 right there. B is 3893, that's B. Number 2, sorry, we'll back that out. And block load at the anchor plate is 1946 or 47, so that's a 1 there. And line pull at the winch, and that is number 4, that's 4500. Okay, excellent. Now here's the question of the day. Let's go back to that drawing just for a second, and I'll let you know how to work on that last workshop. Let me bounce this out a bit. We'll get rid of a bunch of this stuff. All right, so let's see. Here's the question. If we get rid of these anchor plates, and because I have the magic pen, I think I can do this, and get rid of this one, and get rid of this one. And let's see. Let's get rid of these guys right here for just a second. We're just going to take these to 2 anchor plates. Let's just do this for a second. All right, so this is the bunny trail. Hang in there with me. We're going to get there. Elmer Fudd will be showing up right there with us. So, all right, so if we wanted to, if we were restricted for location of anchor plates to something like this, we might have an oh my goodness moment that could kind of get us in a big honking world of hurt here. So if we went really flat like this, hoist strings there, slings, etc., hoist strings here, slings, etc. Now, you know what happens here? We're trying to drive, in this case, we got rid of everything else. If you remember, that was 7785, and I'm just kind of winging it here for a minute, but you know what can happen is these now, instead of, you know, there's no mechanical advantage in any of these things. We were just able to step that load value down by sharing it to pup blocks and anchor plates. But the flatter that blue sling gets in its, what we're going to call the angle to horizon right here, the flatter that gets, what happens to it? Does it increase in tension or decrease in tension? Excellent. It increases in tension. So you want to be really cautious. We would know if you do a lot of rigging here, we would be anticipating, you know, ideally if we could go down to 2 little plates, we could divide that by 2, and you know, in effect, straight away from each one, we're going to have what that number was 3893. But at 30-degree angle from the horizontal, what happens? Remember the load factor for 30 degrees? I can take you right to the master rigger card right here. Here's the master rigger card front panel 1. Here's 30 degrees. Our length to height ratio is 2 to 1. And we'll take length of 2 times height of 1 times share of load. And we're going to be right over here, we're going to be, that's 3,800 times at 30 degrees, it's times 2 divided by 1, and we're clear back up to 7785. Oh my goodness. So there's 7785 in this sling, in that line that's going to those anchor plates. And we just blew up our 5,000-pound anchor plates. You see what happened there? So that's how easy and fast, because these are max rated at 5K, and we're now over 70, almost 7,800 pounds. We're just grabbing 2 of them, just using 2 of them, and we're only because of location and spread and obstructions and all kinds of stuff. The guys decided we can only put in 2 anchor plates. They got to be far apart. Really bad idea. Really bad. And there's a lot of solutions we can come up with how to resolve or how to lower that. But I got to tell you, this we can put in multiple blocks and new plates and so on. But to just stretch one sling to jump from this anchor plate up and through and create that 30-degree angle right in there is a huge mistake. We'd be up almost approaching 8,000 pounds. I mean, it's just, we'll be pulling plates off the floor pretty quickly. So, all right, very good. There is an answer key to this, and what I'm going to ask you to do, Jonah will be back online with us in just a second, and there is a 4th workshop, or last workshop, and it's fairly involved, nothing that we couldn't do or haven't done in part or parcel. But the answers for all of these are on the link that Jonah will have for you or is provided for you, and we'll be able to resolve or solve all of the elements with this very last workshop. We're really getting out of time here, and I don't want to overextend our welcome. We appreciate everybody hanging in there with us. So get the link for the answer key, and I do want to leave some time for question and answer. So as we go along here, so Jonah, can you help explain, if you're back online with me, Jonah, any questions as we've gone along here, and can you help us with the answer key for the workshop?
Yeah, this is Zach, by the way. I wanted to make one announcement prior, and Jonah's got. There actually weren't too many questions that came in. They probably didn't have a lot of time to ask, but there were a few on P30. But he was able to answer several questions as they came up. But what I wanted to announce before we jump into the one question, and Jonah will mention the answer key, I'm going to take control of the screen. And this is really because all of you are interested in this subject. I wanted to make sure you're aware of basically a new program that we're rolling out here. And let me get rid of this here. This is our Fundamentals of Rigging Engineering. We just actually released a press release today. This is a website we've built for the program, but a lot of the subjects you're covering today, like basically horizontal rigging systems, are covered in depth in this course, as well as our Master Rigger course. But this is really one of a kind. I mean, there's nothing like this in existence yet in general industry. We have about 14 industry-leading engineers as instructors that are involved. Keith Anderson recently released a book called Rigging Engineering Basics. Marco Van Dahl is on heavy transport. A lot of people involved here that I want to make sure you're just aware of. You can go check out the website. But the courses, and for instance, the material that you went through today, we have an alternative load handling equipment course. It's about 3 days, and it involves a lot of different types of load handling equipment, like strand jacks and telescopic hydraulic gantries. But horizontal load moving systems is involved pretty heavily as well. So there's about 4 or 5 required courses, and then several electives to choose from. ASME is going to be involved with this from a kind of a CEU's point of view, but again, we just want to make sure you're aware of this because of the subject matter today. And the last thing I'll mention is it's going to be all online and on demand. We're actually doing lecture recordings with all of these gentlemen that you see here. We have people from Fluor and Bechtel and Mammut and Wireco, Barnhart Crane, General Dynamics, Electric Boat, a lot of great people involved. So I'm going to turn it back over to Jonah regarding there's one question I think we got to cover off on, and then he'll help get the answer key out. But again, I see questions actually coming in on this program now too. But Jonah, why don't you cover off on your guys', looks like back on workshop 1, Mike, there was a question from John regarding the angle on the lead line. Does it come into factor? So I don't know if are you going to pull up the previous workshops and we'll make you presenter again?
If Jonah wants to turn it over, sure, I can work to do that. And then let me get my screen up and make sure that is my screen in view, guys?
Yep.
Okay. All right, and let me go back to number 1. Let's see, we're back. Is that the one in question, I think, was the first workshop?
Yep, that's the one.
All right, and the question is the angle affect the line pull on the big beam? Is that sort of the question?
Yeah, the lead line, does the angle of the lead line come into effect at all?
Yes, it does. And what happens here is that if we could get this lead line, if we can increase this angle, let's just say it's 15 degrees right now. If we could get it out further to 50 or out further to 90, we're constantly lowering the down force or load to the high beam. So as we've already discovered, as we straight down, we're going to just simply, it'll interact with that block and be a direct down force. But if we can get it further and further and further, if we went over to a column to another block and then down to a butt block and over, if we could do that, we'd definitely be reducing that one part of line pull and its force and effect on the big beam. So anytime you can open that up to a wider angle, it will lower the force on the big beam. Great question. Great question. Okay.
All right.
Any other questions on our workshop or any others on the rigging engineering program?
No, I don't think so. There was a couple questions regarding ASME P30, and what Jonah's going to do is reach out to that individual after the webinar. So
okay.
I'll just make an announcement there. In the chat box, I did put in there, it's riggingengineering.com is the URL for that program. We're actually running a special promotion. It won't be available until January 2015, but we're going to have an intake group of about 30 to 60 people that we're going to heavily discount it. So if anyone's interested, shoot Mike or myself an email or visit the website and you'll be directed to what to do. But the idea is we want to get some immediate feedback from different users and understand how they enjoyed it and what how we can improve it, whatnot. But I guess besides the work that program, Mike, I'll turn it back over to you to close it off. And thank you guys all for joining us today.
Okay. Very good. Well, I just had a marvelous time today, and I really appreciate the participation. And you guys, everybody hanging in there with us and having a fun day. Little brain teasers and some working our applications and problem-solving muscles. And so it's been a fun time for me. Be looking for the next webinar published to be soon by ITI, and Jonah and team will be getting the notice out for that. I really appreciate you joining me on these things. They're just a lot of fun. I get to meet a lot of you on the road, and please, if you see me somewhere, I'm going to go to the AEMP deal down in Las Vegas prior to the Con Expo this next week. I'll be there on Monday speaking at a panel. But if you bump into me, and if I just don't happen to know your name, you know, just introduce yourself, and I just sure love to put a name and a face together. And I look forward to continuing to work with you. And I learned from so many of you, and I do appreciate your contributions over time. And it's just been a great relationship, and I look forward to us to get old in this business together. I got a long ways to go, and let's have some fun. So have a great day and a great week, and I look forward to talking to you soon. Jonah and Zach, if you're not online, that's great. But we'll go ahead and close out now, and thanks everybody, and we'll be talking to you soon. Bye-bye.
All right, thanks, Mike. One question, too, came up about the answer key. Jonah will be emailing that out, I think, within minutes. So appreciate it, Mike, and everyone have a great day, and we'll talk to you soon. Thank you.